Hello, this is the third video in the Algorithm 2 series on efficiency and complexity and looks at the efficiency and order of networked algorithms. To compare how well network algorithms perform, we generally want to determine the order of the algorithm, and this is usually based on the worst case scenario for the algorithm. So we're going to look at this in terms of the number of vertices or nodes in a network. What would be the worst case for a network algorithm? This would be if all the vertices were connected to all the other vertices. In other words, a complete network. In the worst case for Dijkstra's algorithm, we will work through all the vertices of the network, making comparisons at each with all of the vertices that have not yet been permanently labelled. Thinking in this way leads us to say that the time needed is proportional to n-1 plus n-2 and so on down to plus 3 plus 2 plus 1. As we've seen this before, it is the sum of natural numbers or triangle numbers, which is a quadratic function. So Dijkstra's algorithm has quadratic order. We can write this as O(n squared). Note that some references say that if Dijkstra is used repeatedly to find all the shortest routes in a network, it may be said to have a cubic complexity, but the OCR spec mentions quadratic. Both Prim and Kruskal's algorithms are iterative processes that work through a network making comparisons. If we think of a complexity as a function of a number of vertices, we find that both are order n cubed, where n is the number of vertices. In some references, you may find an alternative approach, which finds the function of a number of arcs, as these algorithms focus on choosing arcs. In which case, both are of quadratic order. But please note that the OCR spec states students are to know and use the cubic order as a function of a number of vertices. No proofs are required, but in general, please be careful and read the question with regard to order given. This is an example of a type of question you may be asked. So, a route optimization algorithm has cubic order. A computer using this algorithm to find the result for 150 locations on a map takes approximately 1.5 seconds. We need to calculate approximately, or in other words, estimate how long it will take if there are 2,000 locations. We could write this as E is proportional to n cubed in terms of the efficiency because we know the cubic order. If we know that n for the first list was 150 and that the time was 1.5 seconds, then if n is now 2000, the difference of a scale factor is 40/3, and therefore the second time is going to be 40/3 cubed times 1.5 seconds. This turns out to be about 59 minutes, or if you wanted even rougher calculation, you could say 1 hour. Here are some additional examples. So with Dijkstra, we know that we are talking about a quadratic, so we say it's proportional to n squared, in which case we know that the scale factor from 50 nodes to 150 is 3, and so we would say 12 times 3 squared, which would give us 108 seconds. Similarly, in the second example, we know that Prim is cubic order, so we would have that E is proportional to n cubed, and for 1,000 to be increased to 5,000, we have a scale factor of 5, and therefore we have 20 seconds times 5 cubed, which is 2,500 seconds, which we may wish to say is about 40 minutes. This is the last video of the Algorithm 2 series.